Welcome to Pre-Calculus. In this video, we're going to continue to tackle limits, specifically evaluating limits with properties. So let's get right to it. So limits are great, right? We all love limits. We've learned so far how to use tables to evaluate limits and how to use graphs. And everybody loves graphs. They're really, really simple. But now we want to focus on finding limits using algebraic techniques and properties of limits. So basically, we want to be able to find a limit without looking at a graph or without touching a calculator. So that's going to be the end goal. And the only way to do that is by using algebra. So hopefully you're really good at algebra and you're super excited to get started. And that's what we're going to do. And I think you're going to find that what's talked about in this video is actually quite easy. All right, so let's learn a couple of the properties first. We're going to learn a bunch of different properties and how we can use them to help us find limits without graphs. So this is called the limit of a constant function. This is a property dealing with a constant function. So a constant function is just a straight horizontal line. For example, generically that'd be f of x equals c. So if f of x equals 5, that's just a straight horizontal line at x or at 5, at f of x equaling 5, which is y equaling 5. So here's the rule, right? It's a really simple property. The limit as x approaches a of a constant function, again, just generically c, is equal to c. So if you have a straight horizontal line, the limit of any value is always going to be c. So regardless of what x is approaching, it doesn't even matter. The limit of any constant is always that constant. So let me explain this let me kind of prove this to you with a graph. So here's that example of f of x equals 5. So this is a graph with a horizontal line at y equals 5. Y is always 5, right? That's what it says. Y is always 5. All right, so notice that if I ask you about any limits, if I say, what's the limit as x approaches 2 of this function, which, of course, this function is 5, right? So we'd be saying, what's the limit of 5 of x approaches 2? So notice you could draw that dotted line at 2, and as we approach 2 from the left, as we approach 2 from the right, we are getting closer to 5. But that would be true no matter where I looked. So if I looked at the limit of 5 as x approaches negative 4, well, it's the same thing, right? Here's negative 4. Right side, left side are both approaching 5. So because it's just this standard straight line, horizontal forever and ever and ever, it doesn't matter what value you approach, you're always going to get 5. So that's a pretty simple property. So let's use it real quick. These problems are so easy. All right, what is the limit of 6 as x approaches 4? Well, 6. If the function is always 6, you're always going to approach 6. Okay, what about the limit of negative 8 as we approach 3? Well, negative 8. That's what the property says. This function is always negative 8. It's never going to change anything else. So the limit's always going to be negative 8. And what about the limit of 22 as x approaches negative 7? You guessed it, 22. Because again, it's a straight line at 22. So it doesn't matter where you approach, you're always going to be getting 22. Pretty easy. All right. The next property is the limit of the identity function. Now, hopefully you know this, but if you didn't, the identity function is y equals x. F of x equals x. That's the identity function, x. And it's called the identity function because it means y equals x. So if x is 5, y is 5. If x is 3, y is 3. If x is 22, y is 22. It reflects itself. All right, so this is such an easy rule. So it says the limit of the identity function x as x approaches a is a. So simply put, the limit of x as x approaches any number is that number. Easy. So whatever number you're approaching is your answer. Now, let's explain this graphically as well because it can be a little bit confusing. But here we have the line y equals x, which is called the identity function. So for example, at 1, you have a point at 1. At 2, 2, 3, 3, 4, 4, negative 1, negative 1, right? Every x has the same corresponding y. But check this out. If we do a limit as x approaches, let's say 3, of the function x, well, here's 3. And if I approach 3 from the left, if I approach 3 from the right, I'm at 3. And again, that makes sense because the y value that corresponds to x being 3 is also 3. So no matter what value I ask you to approach, you're approaching that value. So again, if we approach -2, well, the left side of -2, the right side of -2, they come together at -2. So again, no matter what you're approaching, that's your answer. So here's some really simple examples. What is the limit of x as x approaches 4? Well, 4. What is the limit of x as x approaches pi? Now, don't let this be confusing. Pi is just a number, so your answer is pi. If you want to round it, 3.14. What is the limit of x as x approaches -7? -7. Again, it's pretty simple because it's a line. It's the identity function where every point on the line, the x and the y values are the same. So if you're approaching pi, then your result is also going to be approaching pi. Your y value is. So pretty easy there. All right, the next one is the limit of a sum. This one looks a little bit confusing, but it's so simple to use. So basically, if we have two limits, so if we have the limit of the function f of x equals L, and the limit of a different function g equals m. So we're kind of establishing two limits here. So the limit of function f is L as we approach a, and the limit of g of x is m. So if we're going to find the limit of the sum, f of x plus g of x, well, then we could just basically separate that. That would be the limit of f of x plus the limit of g of x, which would just be L plus m. Because remember, L was the limit of f of x, m was the limit of g of x. So ultimately, this is really a kind of a confusingly written property, but it's really simple. So the limit of the sum or difference of two functions equals the sum of their limits. So if you're trying to find the limit of something plus something else, all you got to do is find the individual limit, find the limit as we approach f, find the limit for g, and add those two limits together, and that is your answer. So I hate showing this. I dislike teaching this because it's a little bit confusing, but when we do examples, it makes so much sense. Let's look at some examples here. So we have the limit of x plus 9 as x approaches 4. So all this property says you could separate that addition. So we can find the limit of x as x approaches 4, and we could add to that the limit of 9 as x approaches 4. We're basically just separating it, right? And again, now we can use the other properties we learned. So the limit of x is whatever value you're approaching, so that would be 4. And the limit of a constant 9 is always just going to be that constant 9. So the limit here was 4, the limit here was 9. 9 plus 4 is 13. There's your answer. So simple. All right, this next one is subtraction, but the sum rule also works for differences. So it'd be the limit as x approaches -2 of 4 minus the limit as x approaches -2 of x. And once again, we just have to use the properties we've learned so far. So the limit of a constant 4 is just going to be that constant. The limit of x is whatever value you're approaching, in this case, -2. So 4, whoa, I did something wrong there. I'm so sorry. Almost made a big mistake. All right, again, it was a minus sign right in between. So it's 4 minus -2, which is going to turn into a positive 6. 4 plus -2 is 6. So hopefully you understand that. Let's do one more here. The limit of x plus 7 as x approaches 9. The property simply says that we could separate that. So we can talk about the limit as x approaches 9 of x plus the limit as x approaches 9 of 7. And then we just have to use the two new properties we learned. The limit of x is whatever value you're approaching. So that would just be 9. The limit of a constant 7 is just that constant, in this case 7. 9 plus 7 is 16. Pretty easy rules. All right, let's keep going now. Let's talk about the limit of a product. Well, it's actually just like the limit of addition, but with multiplication. So if we have the limit of f of x as x approaches a equals L, and a different function has a limit as x approaches a of m, then if we're multiplying f times g and asking you to find the limit, then we could separate that. We could do the limit of f times the limit of g. Well, that would just be L times m. So again, it's kind of confusing to write it down, to actually see it generically. It kind of just looks weird. But in other words, it's really simple. It just says the limit of a product of two functions equals the product of their limits. And this is actually also true for division as long as the denominator is not 0. Because we all know that when your denominator is 0, you have a problem. But anyway, let's look at how easy this is. And again, we're going to actually use the rule and then use our other rules to help us with it. So simple, so simple. So once again, this is the limit of 3x. Well, I could separate that to the limit of 3 times the limit of x, both as x approaches 4. And then again, I said, well, wait a minute. Well, the limit of a constant is just that constant, 3. The limit of x is just whatever you're approaching, which is 4. So 3 times 4 is 12. So simple. Here's another one. So we're going to separate this. It's the limit of negative 5 times the limit of x, of course, as x approaches negative 2. And we're going to say, all right, well, the limit of a constant is just that constant, so negative 5. The limit of x is the value that we are approaching, which is negative 2. In that case, we get positive 10. And then now this last problem actually incorporates a couple different rules altogether. But let's see here. So we have 7 times x. That's going to be the limit of 7 times the limit of x. And then we have subtraction, so we can subtract the limit of 2. So it's really just separating everything. Now, I know that this seems like, oh, I got to show all this work. No, get ready. I'm going to teach you guys a really nice shortcut here shortly. All right, so once again, the limit of a constant 7 is just 7, times the limit of x is whatever value you're approaching, so that's just 5, minus, again, 2 is a constant, so the limit of 2 is 2. So we get 35 minus 2, which is 33. All right, pretty easy, but let's try to make this even easier. You're going to like this. This next rule is called the limit of a polynomial, and this is awesome. It just says that the limit of a polynomial function f of x as x approaches a is equal to just plugging a in. So I know that this seems like it might contradict something that I said multiple times. And I've said that what happens at a is not necessarily reflective of the limit as x approaches a. And that is true as long as there's no problems. As long as there's no holes, no asymptotes, no jumps. This is true. That, you know, what happens is that when you plug a in, if you get a number, that's your answer. Because if you plug a in to your function and you get a number, it means that there's no jump. It means that there's no hole. It means that there's no asymptote. And polynomial functions have no holes, have no asymptotes, have no jumps. So that is why to find the limit of a polynomial function, all you got to do is take that a value and plug it in. It's that easy. So this is going to save us so much time. We no longer have to look at a graph. We no longer have to use our calculator or make a table. So to find the limit of 2x squared minus 5x plus 4 as x approaches 4, all we have to do is plug 4 in. We actually have a name for this. We just call it direct substitution. You directly substitute that value in for x. Now you do have to do the algebra here. 4 squared is 16. 16 times 2 is 32. 5 times 4 is 20. So we got to do 32 minus 20 plus 1. 32 minus 20 is 12. 12 plus 1 is 13. There's your answer. Now, once again, I don't want to contradict what I've been saying, because some kids will say, well, you said that the limit is a different question than asking you what happens at 4. And all you're doing is plugging in 4. So isn't that what's happening at 4? Yes. And listen, what happens at a value and what the limit of that value is could potentially be 2 different answers. But here's the deal. Here's what you got to understand. You only get 2 different answers if there's an issue, like a hole or an asymptote or a jump. But polynomial functions don't have those things. So with polynomial functions, what happens at 4 is the same thing as when you approach 4. That's why to find the limit, all I had to do was plug in 4. Again, it's called direct substitution. Just directly plug it in. So this next one's another polynomial function, and I want to know what's the limit as x approaches negative 2. All you got to do is plug in negative 2. So we get 5 times negative 2 cubed plus 3 times negative 2. Take your time with this one. Negative 2 cubed is negative 8. It's negative 2 times negative 2 times negative 2, which is negative 8. 3 times negative 2 is negative 6. Multiply first. Negative 5 times negative 8 is positive 40. Plus negative 6 is 34. So my final answer there is 34. So let's talk a little bit more about that direct substitution. Again, this is the best strategy to always start off with. And it's simply plugging into the function to evaluate the limit. You're plugging a into the function. So listen, if you are tasked to find a limit of a function as x approaches a, and you don't have a graph to look at. You don't have a calculator to use the table feature. Literally, all you have to do first, this is the first thing you should always do, is just plug A in. See what happens. I cannot promise it's always going to work, but, sorry for the typo there, but if it does work, it's easy. Now, here's why, and I want to make sure I say this for the third time. If a function is defined at x equals a, and the limit as x approaches a exists, and those two numbers are the same, it just means that direct substitution works, right? So if you plug a into your function, and the result is a value, a number, well, then that's your answer. And again, what that means is that there were no holes, no vertical asymptotes, no jumps that would cause problems. So if one of those problems occurred, then something weird would happen. You wouldn't get a number. For example, if you plug in a and you get 0 in the denominator, well, that's an issue, right? That's a problem. We would have to further explore that. Or if you get 0 divided by 0, 0 on top and in the denominator, then that's a problem that we'd have to explore. But, you know, I want to really make sure that I end this very easy lesson today by just simply saying the first thing you should always do to try to find the answer to a limit is just plug A in, right? Especially if you don't have a graph, especially if you don't have a calculator. Plug A in. If you get a number, that's your answer. So yes, I taught you a lot of great properties, a lot of great things in this video, but I'll kind of be honest with you. Maybe I shouldn't say this, but they're really not needed if you just plug A in. You know, if you go all the way back to even like these examples here where we're talking about just, you know, the constant rule. Well, I don't care that you know the constant rule. If you plug 4 in, guess what you get? 4. If you plug pi in, guess what you get? Pi. If you plug -7 in, guess what you get? -7. Even the constant property, it works, right? Because, oh, where do I plug 4 in? Oh, there's nowhere to plug it in. There's no x. So what's my answer? 6. Because if there's nowhere to plug it in, then your answer is just 6. So even the constant rule makes sense with direct substitution. So just use direct substitution, guys. Listen, it's that simple. Even, you know, when we were talking about, look at this, look at it. You don't have to do all this work. I'm not asking you to show all this work. I was just explaining how the property works. But listen, here's what I would do. If I was given this problem on a test or homework assignment, I would plug 4 in. If you get a number, it works. 4 plus 9 is 13. You're done. Plug -2 in. 4 minus -2 is +6. You got a number. You're done. Plug 9 in. 9 plus 7 is 16. You're done. You got an answer. That's direct substitution. It doesn't always work. And in the next video, we're going to talk about what to do when it doesn't work. But listen, if it works, you're done. So how easy is that? But in the next video, we're going to talk about, okay, what do I have to do algebraically if I don't get a number with direct substitution? And yeah, that's going to require a little bit more work, but let's start off with the easy stuff in this video. So hopefully I ended this video in a very good way that makes it very simple for you to find a lot of limits.